All right, everyone. 4 minutes late. Sorry about that. I have to find my adapter to plug it in. My laptop is running out of battery. So this class teaches you how to interface microcontrollers, including Arduino and other microcontrollers with sensors, actuators, motors. It's super practical. And after this class, you can check a lot of boxes on your resume. Same to FPGA and digital electronics and robotics too. It's just important. A lot of students just, this is the only class that we focus on PCB design. And I think we are going to do some like 2 or 3 PCB design in robotics too. We are taking that in the future. But this one is really the fundamental one that teaches you how to make a PCB out of it. So let's look at the website first. So you know the website is electronics.com. And here's the schedule for all the labs. And the first 2 weeks, I haven't changed it yet. So this one should be here. I'm going to give you more time to work on it. Okay. So the first 2 weeks is going to be a PCB design for a power supply. Because power supply is so important, every time you start designing a system, the first thing you have to think about is power supply. Okay. And the Arduino module has a power supply like this. And definitely you cannot, even though it's providing 5 volts DC voltage to a lot of things, but definitely you couldn't just directly plug it in as long if you see that the system is requiring 5 volts. Why is that? I have to consider something else, right? This is 5 volts, and there's a microcontroller requires 5 volts, or a sensor requires 5 volts, and you think that I can directly just use it to power it up. Wrong. Why? The current, the power, right? So what is power? What's the unit of power? Watts, right? And watts is voltage times current, okay? And this one is only 5 volts and 1 amp, but usually you don't want to use 1 amp as a upper limit. Usually 600 milliamps will be the maximum you want to get out from this one. And you can see that there are 2 power modules. These are the voltage regulators, and one is 5 volts 1 amp, another one is 3.3 volts 1 amp. So this power module is a PCB board, can supply either 5 volts or 3.3 volts. And how that works, let's take a closer look at it. Okay. And you can see this is the breadboard, and we got a power, ground. Okay. So quick question: are they shorted together internally on the board? No. That's just independent rails, power rails. Okay. And you can see that this is plus minus. Okay. And you can choose to deliver different voltages to these power supplies here. Here's a jumping wire. It's nothing but a shorting circuit, just a wire, right? And if you put it here, it's delivering 5 volts to here, to the output. If you put it here, then it's going to deliver 3.3 volts to the output. Okay. If I do this, which 2 headers are being shorted together? These 2 or these 2? These 2, right? So I just put a jumping wire to connect these 2 pins. And then I plug this in to the board. Well, you can have 2 ways to plug it in, right? You can do this, pay attention to it, or you can do this. Which one is the correct way to do it? Which one is the right way to do it? Other side, because you can see if you do this, the minus is being aligned to the right rail. Usually we use the red line as a power line as plus, and the blue line is a minus. But right now it's like plus is being shorted to the blue line. It's okay, it's going to work, but you just don't want to do that. Just follow the rules and put it back this way. Okay. And now if I power it up using a adapter here. I can plug it in and deliver some kind of voltage. We're going to talk about that pretty soon, okay? And then it's going to deliver 3.3 volts to this line here. And what's the voltage going to be delivered to here? 5 volts, because 5 volts is being shorted to VCC. And then it's going to be delivered to this power line, to the output. Any questions by far? Okay, one quick question. If I plug this board onto the breadboard, are these two shorted together? I mean the 2 minus lines, are they shorted together? I know. Let me grab a multimeter. You can take a look at it and think about that.
All I hear is I look over and like, oh, that's full volume.
So now here the question is, if I plug this board on the breadboard, is this one and this one, are they shorted together? No. Wrong.
What? They are?
Wait, the two lines.
Shorted. One's on 5 volts.
Here.
Oh, the grounds.
The two ground lines, are they shorted together?
Yeah.
But they were not shorted together before I plugged this board onto the breadboard. But now they are. Let me show you why. So here's a multimeter, how to use it. You can probe voltage, probe current, but now I'm gonna probe the continuity of the circuit. It's gonna be here. Right, is that ready to check the beeps or not? You know the multimeter has 2 probes, right? Is it beeping? Ready? Ready? Yes. See here, this symbol shows that it's activated the beeping function, the continuity checking function. Right? So whenever you have a short circuit, it's going to beep. Very handy function. So now I'm going to check what? Where's the flashlight? Oh, sorry. Yeah, thanks. That's why I drain the battery out really quickly every time. Because I'm going to remove that button after this class. Yeah. What I'm going to do, what I want to check, if these two ground lines are shorted together, from here, right? Did you hear that? So they are shorted together. If I unplug it, these 2 rails are not shorted together anymore, right? So what does that mean? The PCB board has only 1 voltage node for the minus pin or the ground pin. So the cathode of the voltage regulator is being shorted together as a ground line of the circuit, of the entire circuit. That's what we usually do in circuit 1. We just short all the cathode to the same point, so we have a baseline as a ground. You must be confused at what is a ground. Ground is not the ground here, right? It's ground is a voltage reference. Ignore the name of it. So ground equals voltage reference, which is 0 volts. Make sense? Okay. If I plug this back in, and here's a switch, you can switch it on and off, okay? And here's a header, it's called jack header. It's a very common power header. And you plug it in, you can deliver a voltage to the board, and then the regulators are going to regulate it to a certain voltage. One is 5 volts, one is 3.3 volts. Okay, And you can see that there are more headers on the male headers on the board. Take a closer look at it. It's these male headers. And if you don't want to get the voltage supply to the breadboard, you just want to use some of the female headers, the jumping wires, to get these voltages from the board. You can plug in to the board and don't have to switch this to anywhere. You can just directly plug in. You can see 0.3 volts, 5 volts, and all the headers on this column is a ground pin. It's just minus, right? It's like a battery. You got a 0.3 volts plus and the battery minus the cathode of the battery. So you can supply the voltage to all the places just directly using these headers on the board instead of here. Okay. So this module is designed for this breadboard. You can see they had the same dimension, otherwise you couldn't plug it in like this. So you guys are going to design a power module in the first 2 weeks that delivers 5 volts, 1 amp, 3.3 volts, 1 amp, and I'm going to show you in the tutorial other types of voltage regulators that supplies 5 volts and 3.3 volts, but at 3 amps. Okay, because most of the wireless modules are requiring more than 1 amp because they have to do the RF stuff, which is really power consuming. So this one is not really good at managing all these ESP modules, the microcontroller modules we have in the lab. For example, sending signals to ThinkSpeak, which is IoT server that it can sense the temperature and send it to that website so you can monitor it in real time. So it is communicating with a router in the building through Wi-Fi, and then the Wi-Fi will send it to the internet. So that one requires 600 to 700 milliamps, whenever it's sending signal. So the 1 amp module is not really good at doing that. So if you use the IR camera, you can see it's getting pretty red and getting hot. So that's when you design the PCB board, right? After you solder everything on it, plug it in, power it up, and turn it on. You want to turn on that IR camera and look at which one is struggling. It's getting red and hot. Then you probably want to change your the power strategy on the board. Change the regulator to a bigger one. And that's a USB port. You must be wondering, why do we need a USB? Are sending data out of it? We're receiving data from 5 volts? Why do we need the data from a battery? It doesn't have any data in there. So why do we need a USB port? It's power. So what's the voltage for USB? 5 volts, always. That's why we need a standard. It's universal bus, serial bus, right? Universal serial bus, USB. Every time, it doesn't matter it's a USB like this or the mini USB, micro USB, 5 volts. Keep in mind, in the interview, they ask you like, what's the voltage for USB? You say like 9 volts. 5 volts, always, okay? And what's the voltage should be delivered to here in order to get a 5 volts out? So plug something in here, right? So are you sending a AC voltage or DC voltage to this port? DC voltage. Okay, how do we get DC voltage? All of you have taken circuit 1, right? Yeah. So why do you need a DC voltage instead of AC as an input? So what is AC voltage? It's like a sine wave. Okay, and you got a 110 AC sine wave from there, right? Can I directly just plug it in here to here? No, it's gonna burn it. Okay, it's gonna fry it. So AC voltage, you need all these bridges, the voltage bridges and transformers to step it down to the lower voltage, and rectifiers to rectify it to a DC voltage. But we don't have it here. It's just a DC circuit. There's no rectifiers. So it has to be a DC voltage. You must be wondering, hey, we got a DC voltage. Why not just directly provide a DC 5 volts to here? Why do we need all the stuff on the board? It's already DC. Why do we need like 5 volts, 3.3 volts again on the board as regulators on the board? Yeah. Yeah. So that's correct. And for example, this one is very versatile voltage power supply module. I want to supply like 5 volts, 3.3 volts, can be even 6 volts, 9 volts to somewhere, right? And I can only have one plugin, just input one type of voltage. It's going to regulate it to different type of voltages. And that is that this voltage should be higher or lower than the regulated voltages? Higher. It should be higher than the targeting voltages being delivered to the output here. Okay, because these regulators are not ideal. It has a dropout voltage. Which is the voltage loss whenever you regulate it from a higher voltage to a lower voltage. So if you're getting 5 volts, which is your target voltage to be delivered to the output, then these regulators are super cheap. You know, so the dropout voltage is usually like 1.2 volts or something. You can check the data sheet to look at it. So you need at least 6.2 volts here in order to get a 5 volts out. You know what I mean? Because this one is going to lose at 1.2 volts. It's not really good. So I'm going to introduce a different type of regulator later this semester. You'll see that some of the regulators, more expensive ones, only has like 0.4 volts dropout voltage for certain applications. So for example, I only use one LiPo battery, one cell of the LiPo battery, and what's the voltage for one cell? 3.7 volts. Okay, and most of the microcontrollers, MCUs, you know, they need 3.3 volts to power them up, to run it. But I only have space for one LiPo battery cell, you know, portable device. And it's a standard. You just couldn't find like 4.2 volts LiPo battery. It's standard. If you need a higher voltage, just put 2 cells in there, which increases space. And you don't have the space for two cells. Portable device. So I only have like 0.4 volts to drop. Can you use this one? No, it's going to drop 1.2 volts, and then you end up with 2.5 volts, which cannot power up this device, right? You have to find a better voltage regulator for that device. That's why every time before you start designing a system, power supply is the first stuff you have to consider, right? Which regulator you have to use? Power, dropout voltage, size, footprint, a lot of considerations. And there's a range for this input. For the regulators, if you open up the data sheet, you can find out it doesn't have to be 9 volts to be supplied to this jet header. I think it's from 7 to 12 volts. No, it's a range. So in that case, you can power it up using an adapter. The adapter you can plug into the wall, and that adapter has a transformer in there and step down the 110 volts to 20 volts AC, and then it's being rectified to, I don't know, like 16 volts DC or 20 volts DC voltage, and to the plug. Then you got 20 volts. I think 20 volts may work as well, but it's not really good. For these regulators?
Yeah, right next to the
Oh, that's right, yeah. 6.1 from 9. So 12 is too much, but I think did we do that 12? I shouldn't use a 12 volt adapter anymore. Okay, so 9 volts is the maximum, and 6.5 is the minimum. Makes sense, right? You got 1.2 volts drop out, so you end up with like 5.3, which is very close to 5 volts. And in that case, you can choose adapter, the output voltage of the adapter to be in that range, right? Will be the safe range to use. I don't know if we have a 12 volts, but if you use a battery, the LiPo battery cells to power it up, how many cells do you need? 2 will be good enough, right? About 3. More than 9 volts. Also works. That's magic. We did 3 cells a lot. Thinking robotics. I think it's fine. all right? So you can use LiPo batteries, you can use adapter to power it up. And now, in the first 2 weeks, we're going to design the power supply, very similar to this one, that you have to measure it. So it can plug into the breadboard like this. So what I want I mean, you can be creative and do the design by yourself, but eventually you have to use switches to turn on and off these different voltages for different current requirements. So eventually you have four powers, different voltages being delivered to the output. 1, 2, 3, 4, right? One is 5 volts, 1 amp, 5 volts, 3 amp, 3.3 volts, 1 amp, and 3.3 volts, 3 amp. So assuming that you already generated all these different voltages from the board by using the regulator, you can refer to the tutorial to look at the circuit design. But assuming that we already have these 4 traces that delivering all these different voltages, and then I plug this into the breadboard, and I want to deliver one of them each time to the rails. How do we do that? Using switches, these ones. I think you don't have to deliver different voltage to the 2 rails if you make it simple. So we don't want to have like 12 switches on the board. If we deliver the same voltage to the 2 sides, okay, we can change it later. Let's just think about that way first. We're going to deliver the same voltage to the 2 sides at the same time. Okay, we're going to use a switch to turn it on and off. So switch, you can see, it has 3 pins and 1 switch on the top. So it's like this. 1, 2, 3, 3 pins. And you move it to the left, it's going to short these 2 pins. If you move this to the right, it's going to short these 2 pins on the right hand side. That's how the switch works. Okay. If I put a switch for this line, here's a switch. 1, 2, 3. And I connect the middle pin to here. I got another switch. 1, 2, 3. The middle pin to here. Then what? You gotta connect these traces to one of the pins. Serious, I just connected to one of the pins. Right, you have to connect to one of them. What's next? What you think? Oh, ground is somewhere else. Ground is all shorted together at some point. You don't have to worry about ground. Ground is always grounded together, right? It's always grounded. You don't have to switch the ground, do you? No. So if this is what we did last year. If you short the other pin of the switch together and send it to the board, for example, here's the board, right? I got plus, minus, and I just send it here. And these are grounded anyway, right? That's the power module. Is there anything else I have to do? So this is going to deliver the same voltage to the two sides at the same time. So if I move this stick to here, just this one, what's going to happen? It's going to short these two, right? It's going to make the connection here. It's going to deliver this voltage here and here. Okay. If I keep it on the left, this voltage is delivered to here, which is shorted to nothing. I only need to switch on the ones that I wanna use and deliver that voltage to here. Right? The other one is grounded. It's grounded to all the ground here, shorted to one common ground. Make sense, right? So how do we have a different voltage on the two sides? Like I wanna use one here and another one with a different voltage. Hmm? Any other way to do it? I'll leave it to you guys, all right? I don't have a solution for now, but just think about it for a couple minutes. Probably we'll be able to find a solution for it. Just be creative. I don't want to just let you know, like, you should do this, just follow and do it. Oh, just deliver different voltages to the two sides, like this one. See, I got two rails, right? One here, one here. I can use this jumping wire to make the different voltage. I got 5 volts and 3.3 volts on one side, and the other side is different voltage. Can I do the same thing or similar thing to choose whatever voltage I want to deliver on each side? Because this one right now, if I switch this on, it's going to deliver the same voltage to two sides, both sides. Yeah, I got to use some of the headers, jumping wires, and switches as well. Don't put too many switches on it. You know, you can extend it, right? You can extend it.
You're right.
You can put more outside. Any questions on this by far? Straightforward. And for the footprints of the surface mount components. This is a PCB board, but also a ruler. I think someone designed a ruler on the PCB board and fabricated with a foundry. It's a PCB, printed circuit board, and they put all the pads on the board and make all these labels as a ruler. So you can use it as a ruler, but also it's can be a reference when you are wondering the size of the different footprint of surface mount components. You can look at it and find out the standard packages easily. These are pretty commonly used packages you can find on the market. Okay, so that's IC flow this time. That's integrated circuit design. When the company like TI or analog devices, these companies are making all these IC chips, including amplifiers or regulators. They are not creating different packages. So these are called IC packages. They have specific names. You can see this one is called SSOP, right? For example, that's the name of the package. When you design the PCB boards in Eagle PCB, you don't have to create the different packages for different sensors each time. So, for example, this package looks like this, right? It has a specific distance between the pads horizontally and also the size of the pads as well. You can find devices using this package. These devices can be amplifiers, can be sensors, can be motor drivers. You know what I mean? It's a standard package, can be used for all different designs. Okay, and same to the other packages. You know, this one can be a CAN bus being used in motor vehicles, CAN bus controller, but also can be an Arduino chip. It's just a package, standard package. Okay. So these are usually inductors, capacitors, and resistors, different packages for these devices. And this looks like exactly like the regulator we have here. Look at this one, the shape of this guy, right? You got one big pin and 3 pins at the bottom. So this package, no difference. Okay, so this is a very standard package as well. You can find in Eagle PCB's library. You can directly use it for other devices. But a lot of times, if you are designing a PCB board and you want to use a component which is not exactly the component in the library, for example, in Eagle PCB, you can find a device in the library. It's called 1117 regulator, which is this regulator. Okay, it's called 117 voltage regulator. But you want to use the device has the same footprint, same package, same footprint. You know, has a pad here and 3 pads at the bottom. It's not a regulator, it's a transistor. All right, and you cannot find that transistor in the library, but you still want to use it in your PCB design. How do you manage it in that case? Okay, so a device in PCB design, there's a device. The device has a schematic and a footprint. So the footprint is the package or package. Sometimes you'll see it's a different name. It's called package. And this one is universal. It has its own name. Like this one, also the name of this ISO-T223. Okay, so a device, for example, in the library is 117 voltage regulator. Okay, so this one has a footprint, has a specific schematic. So when you are trying to create a new device in Eagle PCB, you can directly use this footprint in your new device. You don't have to redraw it. You can directly use that footprint in your new library, and you can draw the schematic if you don't have the schematic for that device, or you can reuse schematic as well at the same time and form a new device and rename it. So you can make a new device without redrawing everything. It's very convenient. Just don't redraw everything in Eagle. It takes a lot of time. That's why you can make a first PCB really quick. And just keep reusing all the different footprint, especially for the capacitors and the resistors. You have a 1K, 2K, 10K resistor in the library, but you are designing a PCB board using 1.1K, 1.2K, 1.3K. Do you have to create every single device in there? No. They all use, for example, 0603 footprint of that resistor, and directly just pull it and get a schematic out of it. Do you have different schematic for different resistors? That's it, everywhere. Do you have to redraw it? So when you are designing a new device or new resistance value in Eagle PCB, you just keep using the resistor symbol everywhere. Okay, just keep using it. And the package is going to be 0.0603, which means 0.06 inches by 0.03 inches, which is the size, dimension of the resistor of the footprint. It's just what we usually use. Right. And you combine them and rename it, right? Rename it and make a new device and name it as 1.2K. So it's fine if you don't have every single different resistance value in the library. You just remake it. So for now, for example, we use the what's the name of the library? I forgot, but we download it from GitHub and upload it to Eagle PCB, and it has maybe like 100 different resistance values. But still, sometimes you need a different value of the resistance. You still have to remake it. So for now, if you use the way I just told you, probably you can make a new resistor in 1 minute or less than 1 minute. Instead of redrawing the package in a layout design view. So which one is 0603 here? This one. You'll see 0603?
Yeah.
So got a concept about the size of it, right? Why do we like 0603? Why I like 0603? Why not 0201? Yeah, all depends on your finger, right? So my finger couldn't really handle that 0201. As you put on the table, it's going to be blown away by your breath. So the tweezer, why not using 005? This one. Yeah, it's too big. It's taking too much space on the board. Like we want to use 0603. It's not too big and not too small. Just about right. For manually soldering something on the board, it's manageable. Okay. We do have a lot of 0805 resistors and capacitors in the lab, but I rarely use them. So starting from a couple of years ago, I started ordering all these devices in 0603. If I'm manufacturing a PCB and not manually soldering all the components to the board, but asking the foundry to do it for me, you can order that kind of service. It just costs like another $50. And they will put all the components to the board after they made the board for you. They have the robot arms to just solder it very quickly.
Is it 50 more for 5 or 50 more each?
It depends on the devices you use, right? Some of the microcontrollers are pretty expensive.
Yeah.
But when you order that kind of service, because these resistors are dirt cheap, so usually these are free. Most of the, like 90% of the components on the board are free. You only pay the expensive ones, like the ICs for microcontrollers or any kind of sensors are more expensive. Op-amps not really. Probably can be free as well. Which one?
The numbers in the parentheses above the 0608.
Oh, these ones?
1603 or whatever.
Yeah. You mean these ones?
No, there's numbers in parentheses like above the resistor names, and it's the measurements for it.
Mm-hmm. Yep, guess so. But why do you have to know the 0603 or 005? Because when you order devices from DigiKey, if you are in a different country, probably it's a different way to order things. But in DigiKey or Mouser, I guess. We want to find a correct thing, and you use these dimensions, inches, order stuff. That's why I want to know these ones if you do engineering in the US.
When you were ordering stuff in China, was it in metric or? I
didn't order this too many stuff in China. But we use the Chinese use metric most of the time. Yeah.
Well, yeah.
Meters, and that's why I have no sense with like inches and foot. The first couple of years. Like I told students, I have to think about the 1 foot long subs when I want to try to know like what's a 1 foot.
I just measured
that's a sub. Okay, let's get back to the tutorial and see what's requirements here for the first 2 weeks. So again, I'm gonna update the website later. All right. So it came here later, so you should know that I have to log into electronics, this website, and then go to microcontrollers, and these are all the tutorials. So this one should be here, and I'm gonna push all the other tutorials 1 week later. Yeah, before you work on this one, you gotta finish the PCB tutorials, which are super simple. I think it's short, a couple of short tutorials here. You go to the website here, the main page, and tutorials, resources, and Eagle PCB basics. And these ones are based on the older version of it, but it's very similar. For example, the name for the package, I think they used footprint or package there, but the newer version use the other name. I just know it's the same thing. It's just the metal plates, the size and distance of these definitions of these different packages. And schematic, it just says, right? You put them together and make the connections. From this one is pin 1, right? And this terminal is pin 2. They just make the connection and make a device in Eagle PCB, right? So follow these ones so you know how to do that. I just give you 1 day to finish all the tutorials here. Very simple. Just finish it, and then you can start working on the other ones. Okay, let's open it up. See, it's pretty long, and the final product is going to be a power PCB module. Then we are going to fabricate a PCB for you guys, for each of you, and let you guys solder it in the lab. So the purpose of that is, first you get to know how to make a PCB out of, how to do soldering with the surface mount components. And also we got a power supply module, because this one only has 1 amp power supply regulators. But later this semester, we're going to deal with some of the Wi-Fi modules requires more current. So you need 3 amp modules. I don't want to keep switching different modules all the time. So we will just design one PCB board, which can deliver different voltages and currents to the board. So you can use your power supply module to power up the sensors and modules later this semester. I think there's an example. So that's an adapter, right? So these are the power components in the adapter. And we are not dealing with the high voltage stuff. So whatever we are dealing with is low voltage electronics, 5 volts, or everything below 12 volts, DC. So adapter here has a transformer, step down the 110 AC voltage from the wall to whatever, that can be 12 volts, can be 9 volts, can be 20 volts DC. Here, this is a jack header, a plug-in to here, and then the regulator will do their job to step it down or stabilize it to a certain voltage for the microcontrollers and other components on the board. Okay, that's the modules picture. And here's a schematic of it. It's a very popular module, so you can find a schematic in a lot of places. And the different capacitors here to remove different frequency of noises. So you can see how they design this circuit. Here's a 5 volts regulator. Here's a 3.3 volts regulator. Why do you have to follow that order? Step down, right, in a certain sequence, because you got, for example, 9 volts here, and so dropout voltage is 1 point something volts. But doesn't mean that it's going to be 9 minus 1.2 volts, right? It's a regulator, it's going to regulate it at 5 volts. It just has to be larger than 6.2 volts. Then there's a range. As long as it's within the range, it's okay. And you got a 5 volts output, and then you use that as the input for the 3.3 volts regulator. Okay? And what is this? LED, yep. What's that used for? Yeah. The power indicator. If you plug in, so you have to know that when you design the circuit, you have to know that the power indicator doesn't indicate that you have a 3.3 volts output guaranteed, right? Because the power indicator is not shorted to here. It's letting you know that 5 volts is already delivered. It doesn't even have to be 5 volts. Something is here. Okay, something is here. It's turning it on.
Oh, are we going to need the USB jack on ours?
Just DC. And that's the design of the headers. You can probably refer to it if you want to deliver different voltages on the two sides. Can be a very good practice. And on DigiKey, you can definitely check the data sheet to find out the footprint. But again, this is very standard footprint. You don't have to remake it, right? Just reuse whatever already exists in the library. Looks huge, like a pillow. And this is 0603, and it's a cap. It's good to know, right? The caps look like this. The resistor looks different. So the caps, even though they have the same footprint, but they look different. Same footprint, but the footprint is just 2D metal pads on the board. You just need the two pads on the board. That's the footprint of the device. But for the device itself, it's different because you can see that they have one metal plate, another metal plate, and this is the dielectric material in the middle to form that capacitor. What is this? Cap. What is this? Cap. Aluminum cap. What is this? LED. Should be familiar with all the different devices, how they what they look like on the board. When you pretend to be a senior engineer during the interview, it works. Oh, here's LED, I know it. What is this? Resistor. See, it looks different, right? Even though they are both 0603 footprint, they look different. That's the material of the resistor, I guess. There are two terminals, connections. What is this? It's a diode. It's a rod diode, through hole, not surface mount, because I have to plug it into the hole. That's a jack header. That's a power, this is plus, that's an anode. These are grounds or cathode. Sometimes these are shorted together, sometimes they are not. Keep in mind, you want to short them on the PCB board. So you need to leave 3 big through holes on the board to solder it on it. Okay. Shouldn't be that expensive. You know, I can buy, you know, just 10 cents, I guess, from Amazon, a big package. This is an example, right? So this is the footprint of it, through 3 through holes. 3 more minutes. See if I can show you one example there. Again, so Eagle PCB is free if you use your school email to register for account. I think if you want to purchase it, about $500 for the whole year, which is, you know, at the first time you're thinking like, I really don't want to pay the $500 to pay that Eagle PCB software to design PCBs. I'm going to switch to Altium Designer, which is more standard industrial PCB designing environment. It's $500 per month. Let's use Eagle. I don't even mind paying that $500 for the whole year. Anyway, but it's free for you guys. There's a limit on the size of the PCB board. It has to be smaller than, I think, I don't know exact numbers, but something like this. It has to be smaller than that. Right. So this is obsolete. Do not follow the PCB layout here because this one does not have the switching functionality here. So I have to redesign it. But this one is able to deliver all of these voltages and currents to the headers. But I didn't consider plug this into the breadboard by that time. But we do have examples from last year. I can show you that students, where's the example? Do I have it? Oh. So I can do it really quickly. I'll try it. This guy. that was probably his first soldering work. Not really aligned really well. But you'll learn how to solder and get a good job.
So this is an update on our power supply, and
okay.
Last week.
I think the breadboard I'm going to give to you will be bigger than this one, so we'll have some space for other things other than just a power supply module. Okay, but this is something you can expect. It's way smaller than this size, so it should be free. Equal PCB. It's only $5 for 5 pieces. Okay. Any questions? Anything? No? Okay. I'll update the website and let you guys know the due dates of this design file. And 2 weeks is the due date for the design files. I'm gonna send it out for fabrication. It takes another 10 days. And probably 4 weeks from now, you'll get a PCB module here. All right.